All right. Awesome. So we're going to be talking about freshwater resources today. I've realized this hour and 50 minutes is a little longer than the class periods I usually teach, so I thought it might be fun to include a couple of jokes here and there. So I study fish, so I look for a couple of fish jokes. This joke might not work with a mask on, but do you know what you call a fish that doesn't have any eyes? You call it yeah, exactly. Probably can't, but anyway. And then one other joke. This, I don't know, this may be, so one fish asks the other fish, why did the chicken cross the road? How does the fish respond?
What's a road?
Yeah. First, what's a road? For that matter, what's a chicken? So, you know, I found this funny. I have a strange sense of humor, though. So if you didn't know that already, I guess now you'll figure it out. And if you have any other, if you know of any other good fish jokes, let me know. I guess some people got that.
I have a bad chemistry joke.
Okay, I like bad chemistry jokes. I was bad at chemistry, so bad chemistry jokes are appropriate for me.
How do you help a sick scientist?
How do you help a sick scientist? I don't know, Jay. How do you help a sick scientist?
Well, if you can't heal them, I guess we gotta bury them.
If you can't helium, then you've got to barium, B-A, right? Okay, nice. Good job incorporating our, if you can't helium, then you barium. Okay. Yes, hopefully you don't want to do that to any of your teachers right now, but who knows? It might have been a rough semester. You never know. Yes, please keep all the science jokes coming. It would be fabulous. Science should be funny. I find it humorous myself many times. So just to review, class last time we were talking about biodiversity loss and what's causing it. Isn't that just like a great transition from funny jokes to like what's causing species to go extinct? Don't you love that? So what were the factors we talked about that are causing biodiversity loss? There are three big ones. There's a good little pre-celebration review. You guys, this is embarrassing because I completely forgot. So you guys are going to have to help me, otherwise.
One, direct exploitation.
Thank you. Yes, direct exploitation was one, right? Things were over-harvested. What was the example of a species that was over-harvested and led to its extinction? Pasture pigeon, So that's one, direct exploitation. What's another one? Introduced species. Yeah, and what example did we use with that? Yeah, the fish, so cichlids, these fish that were eaten by the gigantic Nile perch. And what's the final one? So three things that lead to extinction. So first we talked about was overexploitation with the pasture pigeon. Second was introduced species with the cichlids and the Nile perch. And what was the last one? The last one is actually the biggest one. Habitat destruction. Yeah, thank you. Habitat destruction is probably the biggest one, the most important one. And what species did we talk about with habitat destruction? Yeah, thanks. The ivory-billed woodpecker. It was a bird that needs a big patch of forest to survive. And when those forests were harvested for timber, it was not able to survive anymore. So anyway, yeah, so those are the main three. Introduced species, direct exploitation, and then habitat destruction. I talked about the other day. But it's not all bad news with species and extinctions. We've been able to help some species recover. So the giant panda populations have been increasing for about the last half century. Their populations were really low due to primarily to habitat destruction, but a couple other things. So a lot of attention to the giant panda has caused its populations to be coming back. The Mekong River dolphin, this is a freshwater dolphin, been impacted by a bunch of things, building dams, overharvest of its prey species, those kinds of things. but there's been a lot of effort put on protecting the Mekong River dolphin. And so just last year, data is showing that its population is rising for the first time in 20 years. So been helping that species to recover. And the mountain gorilla as well. In the book Gorillas in the Mist, some of y'all may have seen, again, a lot of conservation efforts put on behalf of the mountain gorilla. It was impacted by overhunting as well as habitat loss. And its population has really been coming back from the brink. In the last 50 years or so, population has doubled. So as much as we have these things that are causing species to decline or go extinct, I don't know, man. That was kind of like Leopold's thing. Like, we're the only species that says, wait a minute, what we're doing here might not be good because we're causing these species to go extinct, and we can work to conserve them. And we've had some real success stories with regards to that. Cool. So talking about water resources today, and you look at our planet, also known as the blue planet, what kind of water do we see on that planet? Salt water, right. Lots of water, but the oceans are not usable as a resource for most terrestrial species. What else do we notice about water on this picture?
Freshwater and clouds and ice.
Yeah, so this is Antarctica, so we've got these polar ice caps, right? We've got a lot of the Earth's water that's locked away in ice caps. Anything else you might notice about this picture and water? There's a lot of it. There is definitely a lot of it. The blue planet, There's one more kind of water you can see here that we haven't mentioned yet. Yeah, clouds, right? So water moisture that's moving around the planet from place to place through atmospheric transport. If we remember back to, I don't know if it was the first day, it was one of the first days we talked about the PCBs and the salmon, right? That one of the ways that those PCBs were moving around was by transport in clouds. So we've got lots of water on our planet in different forms. We've got oceanic water, ice caps, atmospheric water, and it's hard to see. East African Rift Lakes, we have some fresh water that's just barely visible here. So you don't need to write these statistics down, but I think just to give us an idea of, it's the blue planet, but from a resource perspective, water is scarce. So only 2.5% of all the water on Earth is fresh water. And the vast majority of species need fresh water. But even less of that is active in the water cycle. So of all the water that we see on the planet, less than 0.5% of that is actually active in the water cycle. It's moving around place to place. So almost all of the water on Earth is inaccessible to us and other species. Either it's saturated with salt, and so drinking it would actually make us sick, or it's locked away in the polar ice caps, or it's underground. We'll talk in just a moment about groundwater. So really, water is, some would argue, our most precious resource. And so very little of what's on the planet is actually accessible to us. So the good old water cycle, you've been learning about it since high school, probably middle school, right? What are a couple of the things going on in the water cycle, just to review? We've got, so of that 0.5% of water that's moving around on the planet, what are some of the things or what are some of the ways that it's moving? What was that? Evaporation, yeah. So water on the surface of the planet going back up to the atmosphere through evaporation. And then we can start there. So let's say that water's in our atmosphere. So it's been evaporated up off the surface. It's in our atmosphere. Then it can find its way down to the Earth in precipitation. There's a whole song. Does anybody know the water cycle song? If you do, you probably wouldn't let us know because we might ask you to sing it or something. But it's something like, it goes down in precipitation, yes it does. It comes down in precipitation, yes it does. And then it's like, it comes down in precipitation, it goes up in evaporation. Anyway, it just goes on and on. Like the water cycle really does. Okay, so it's up in the atmosphere, it comes back down to the Earth through precipitation. And then when it hits the surface of the Earth, it can go one of three ways. It can run over the surface of the earth as surface runoff in our rivers and streams. It can go back up to the atmosphere, right, from evaporation. Or it can go down into the ground. And there's a lot of, you don't need to know all these terms. We're going to talk about this in very broad perspectives, but it can go down into the ground. And of course, once the water gets into the ground, that's when it can be used by our plant community. So then they pull that water up through their roots, turn that water into plant biomass, into leaves and roots and all that kind of stuff. And then some of that is going to go back up to the atmosphere. You know, plants open up these holes in their leaves called stomata, and they release water up to the atmosphere. So water is in this big cycle of atmosphere, down to earth, back up to atmosphere. And, of course, surface runoff is all going to go down a hill and eventually end up in the ocean, which, of course, is salty. So we have this water cycle. Well, as I mentioned, y'all probably learned about that back in the day, but as environmental scientists, we're really interested in how have people affected this water cycle? How does this water cycle work a little differently now that we've got 7 billion people on the planet, right? So any thoughts? I don't know. What are some of the ways that that water cycle might function a little bit differently now that we've got a whole lot of people on the planet?
Like where I come from now in the Columbia, South Carolina area, we have the Calgary National Park, and it's a lot of swamp.
That's right. You have your friend the alligator, right? Or the snake? Patricia, yes, Patricia in the Congaree, yeah.
But a lot of the cities and towns down there flood during and after the rainstorm because it's not supposed to be a city, it's supposed to be small.
Yep, absolutely, yeah. Yeah, so as this ground gets turned into pavement, the water's not going to be able to go on the ground, it's going to run off the surface. That's one of the ways. Yeah, so let's look at some data here with what happens. So this is a little case study. And again, you don't need to get all the details of this. There's just going to be a take-home message at the end, which you'll all be allowed to take home with you at the end of today's class. So this is where I was teaching for a year. It's just north of Dallas. And so the Dallas-Fort Worth Metroplex was, for a long time, and I don't know if it still is, one of the fastest growing areas in the U.S. as far as population goes. Lots of people moving there. I guess people like Texas. Or people were moving from other parts of Texas to Dallas. I don't know. So in this little case study, we looked at how the amount of water in creeks in this area has changed in the last 40 years. Because remember, water can go 3 different places once it hits the earth, right? It can go runoff, it can go back up to the atmosphere, or it can go down the ground. All right. So here's an aerial photograph. Texas is not actually all red, although there is the Red River. Separates Texas and Oklahoma. This is an image that makes all vegetation show up red. It filters for certain kinds of ground cover. So basically everything in this picture that you see as red, think of that as like plants, like forest, grassland, that kind of stuff. Then this kind of translucent white coloration, that is urban areas, urban development, right? So, you know, you can see it's kind of concentrated here, but then spread out this place as well. And so we looked at like 4 little watersheds. So a watershed is the area of the land that drains down to a particular point, if that makes sense. So when we talk about the Clear Creek watershed, it's all the area of land where if a drop of water falls into it, it's going to drain down into Clear Creek. Right? Anybody know what watershed we live in here? Which watershed Asheville is in? We're actually in a couple watersheds because there's big watersheds and then small watersheds inside them. Yeah. So it's actually kind of interesting. I mean, to me it's interesting. Anybody ever drive down I-40 from Asheville out toward like Charlotte and like Raleigh and all that stuff, Greensboro? You know, if you're driving out I-40, you go past like Swannanoa, and then you go up in the hills, then you go over a hill and you go down, and then you go by like the town of like Old Fort, and there's Marion and all this stuff, and then you get to Charlotte. Okay, so there's that big hill kind of in the middle. Well, here's the deal. We live in the Mississippi River watershed. We also live in the French Broad River watershed because the French Broad River flows into the Mississippi eventually, right? Right here, we're in the Reed Creek watershed because the UNCA campus water flows into Reed Creek. Reed Creek flows into the French Broad. French Broad flows into the Mississippi. Mississippi flows into the Gulf of Mexico. Okay, so we're in the Mississippi River basin. If you go up over the hill toward Old Fort, you go up over the hill on the way to Charlotte, all of a sudden, you're not in the Mississippi River watershed anymore. You're now in the Yadkin-Pedy watershed and then the Catawba watershed. And those rivers all flow east to the coast. I should have a map up when I was talking about this. Those rivers all flow east to the coast. The French Broad River, on the other hand, flows north, meets the Nolichucky, meets eventually the Tennessee, the Ohio, and the Mississippi. Okay, so all these little watersheds. So this is an image from 1974 of all these small little creek watersheds in Dallas-Fort Worth Metroplex. So here's some data on the amount of water flowing out of each of these creeks, right? So this is stream discharge, how much water is coming out of that stream in CFS, in cubic feet per second, right? So this is like the amount of water coming out of these watersheds. Okay, so we've got data from 75 to 2005, and we've got the amount of stream discharge on the y-axis here. And each of these data points is 1 year, if that makes sense. So does anybody think there's a trend here over time? How many people think there's a significant trend over time, increase or decreasing? So as scientists, we use statistics to test the strength of these relationships. And we use something called a correlation coefficient to examine the relationship between two variables. And that's called R. And R can be between -1 and +1. +1 is a perfectly strong correlation. It means when one variable increases, the other one increases. When one variable decreases, the other one decreases. Okay, that'd be a positive correlation. An R of -1 is a perfect negative correlation. It means for a given increase in one variable, there's the same decrease in another variable. So we can talk about variables being positively correlated if an increase in one leads to an increase in the other. The slope would look like this. Or we can talk about variables being negatively correlated if an increase in one leads to a decrease in the other, and that would be a negative slope like this. Okay. And then we want to know if that relationship is strong enough for us to consider, essentially. And so we use something called a p-value. The p-value is the probability of a given relationship occurring at random. And all you need to know is that the lower this p-value gets, the less likely it is to have this relationship occur at random. And so when that p-value gets low enough, we say the probability of this relationship happening at random is really low. And we conclude that, in fact, there's a significant relationship going on. So does anybody know there's a value, a p-value that we use? It's like a cutoff. And if our p-value is below that, we say there's a significant relationship. Anybody know what that value is? Alpha. Yeah, right. So alpha, good. Some of y'all may have taken statistics courses. So alpha is Essentially, and this is going a little deeper than I was planning to, but that's good. Yeah. No, that's cool. No. So alpha is just like how strict we are in deciding if it's significant or not. What I was thinking people might say is that below a p-value of 0.05, we generally conclude that our relationship is significant. In other words, there's a 5% or less probability of getting our relationship due to random chance. So we say, you know what? Random chance is so unlikely, there's actually a significant relationship going on here. So really, all you need to know is that when this p-value is less than 0.05, with just about any statistical test, we say there's a significant relationship. Okay. Now, the reason I went through all that song and dance is because that p-value is going to tell us whether we have a significant correlation between year and the amount of water flowing in these creeks. So we have a p-value of 0.372 here. So is there a significant correlation between year and stream discharge? See, this is when I figure out like if I said it in an extremely confusing way or in an easy to understand way. And as usual, I said it in an extremely confusing way. Here's what you want to look for. If this p-value is less than 0.05, then we conclude that there's a significant relationship between the variables. So in this case, do we have a significant relationship between the two variables? We don't, because it's more than 0.05. Does that make sense? It's 0.372. So if that had been less than 0.05, we'd say there's a significant correlation. I won't call on you, but how many of you have taken or will be taking a stats course? So this might be something, yeah, that you'll deal with at some point again. Anyway, okay, so all right. So in Clear Creek, we can say that the amount of water in the stream per year did not depend on what year it was. There's no significant relationship here. Okay, here are data, again, 1 dot per year for Little Elm Creek. How many people think there's a significant relationship here, just kind of eyeballing it? Do you have any way to decide? No, I'm just asking randomly. I do that a lot. All right, what are our statistics telling us? Do the statistics say there's a significant relationship between the two, or no? No, right? Good, so this is greater than 0.5. Okay, so Little Elm Creek as well. No significant change in stream discharge over a year. How many people think there's a significant relationship in Denton Creek? You're all correct. Again, no change in the amount of water over time. At this point, you're thinking, there's only one more creek left, and we haven't seen a significant relationship. There's probably going to be one. You know me all too well. All right, so here are data for Rolett Creek. And if you just look at those data, what kind of pattern jumps out to you, or jumps out at you in a non-scary kind of way? Kind of looks like it increases, right? It looks like there are maybe lower values here, higher values up here. And so when we test it statistically, we get a really low p-value. The p-value is based on the strength of the relationship between these two variables and then how much scatter there is in our data. So there's a positive correlation here because R is positive, and it's significant. And if we use another statistical technique called linear regression, we can plot a straight line that illustrates that relationship. So there it is. Okay. So for some reason, the amount of water in Rolett Creek was increasing, right, from the late 60s into the early 2000s. I wonder what was going on there. So this is when we might chat in the group, but we'll just have this conversation in our large group. We're like one big group. We're like one big family here. What are some things that could cause the amount of water in Rolett Creek to increase? Let's think of some possible hypotheses for that pattern. What could cause the amount of water in that creek to increase? Any thoughts? Say that again? The runoff, yeah. So increased runoff over the years, increasing runoff over those years could lead to an increase the amount of water. What else? Any other hypotheses? There was a dam failure. So, I mean, there could be, but it kind of increases like every year. I guess if it was like a dam that broke, we might expect like all of a sudden an increase. Whereas this is like kind of a more steady increase over time. Any other thoughts? So, thinking back to our water cycle, right, there's a few things that could be happening here, like just thinking big picture, and these might not all make sense with our example, but just thinking big picture, right? So certainly, like changes in rainfall would affect the amount of water, but would we expect that to lead to the pattern that we saw in our creeks? Yeah, there was only one creek that increased, and those others were pretty close. I don't know if you saw the scale, but you know, they weren't more than 20, 30, 40 miles away from each other. So it'd be unusual for like one creek to get an increasing rain over the 20th century and the others not. So probably not what's going on there. Snowmelt is another thing. It was interesting when I was doing research out in Oklahoma. There was a river. It's spelled like Arkansas, but it's pronounced Arkansas, the Arkansas River. I don't know why they pronounce it that way. That river was in Oklahoma, but it's fed by the Rocky Mountains. So there'd be a peak in the amount of water in that river in the summer just because of the snowmelt. So all these different things. Removal of vegetation, that's going to lead to more water getting into the creek, because when we have vegetation on the land, it's going to slow the movement of the water, and it's going to pull water up out of the soil. So when we take vegetation off, it can lead to higher stream discharge. And then, I don't know if you remember, when we looked at economic reasons to preserve biodiversity, we talked about the ecosystem services and the value of all of them. And if you remember that wetlands were some of the most valuable ecosystems on the planet, one of the reasons for that is because they act like big sponges, right? So they absorb water when there's a lot of rain. They hold it when there's a drought. Do you all know what I mean by wetlands? These are like swamps, estuaries, those kinds of things. Ecosystems that are like they're kind of like half aquatic, half terrestrial. So it could be in the floodplain, yeah. I mean, yeah. So some floodplains will have wetlands and some won't, just depending on kind of like the slope. But yeah, they definitely be in the floodplain, yeah. Mm-hmm. Absolutely, they would. Yeah. So we can talk about you can take. You can take Dr. Landon Ward's wetlands course and learn about bogs versus fens, and some are rain-fed, some are groundwater fed. But yeah, those are wetlands are areas that are saturated with water. Yeah, so they can be pretty important. All right, so to think about Rolette Creek. So here are the watersheds of those creeks that we were looking at. Here's that 1974 image. Here's the 2003 image. The colors are a little bit different, but if I scroll back and forth, what do you notice about the Rolette Creek watershed? What's happening there between 74 and 2003? Yeah, exactly. There's less of the red. And so that red was our vegetation, right? And that kind of silvery color was like the impermeable stuff, all the cement, all the blacktop, all the pavement. So this Dallas-Fort Worth Metroplex, the sprawl kind of like stretched into Rolette Creek. So in fact, that's what was happening. The reason that there was more and more water getting into that creek over the years is because there was less and less going into the ground because it was getting paved over. Just to kind of encapsulate that point here, if we think of an area before it's been urbanized and then after it's been urbanized, I don't really like this cartoon a ton because it says pre-urban and urban as if everything that isn't urban is just like not urbanized yet. But so we can look at the precipitation and we can look at how much of it goes into the ground versus surface runoff versus back up to the atmosphere. And you can see here we have evaporation and transpiration, right? So evaporation is water that is, due to heat goes straight up into the atmosphere directly. Transpiration is water that is taken up by the roots of plants and then out through the leaves. So we've got kind of two different ways, two different mechanisms by which that water is getting back into the atmosphere. But if we look at a pre-urban versus an urban environment, what do we see as a big difference in where the water's going? Yeah, if we look at the runoff, surface runoff was only 10% of the water that fell down back before of the water that rained. It didn't fall. It meant to be rained down. It was only about 10% of all the water that came down in rainfall was surface runoff in more of a forested ecosystem. But now, when it's been urban, 43% is running off on the surface. And of course, that's coming from the groundwater. So about half of the rain used to go directly down into the ground, which is awesome because then it kind of fuels our plant ecosystem. Now, we've only got about a third of it going into the ground and about 40% that's running off, 43% running off.
And there's less evaporation because when all the water runs off, well, there's less water sitting there to be evaporated.
Yeah, so here's the thing about that. Yeah, because it's tricky, right? Because they lumped evaporation and transpiration together. So, there's a lot less plants on the landscape. So there's going to be a lot less transpiration, evaporation, it's hard to say. But yeah, as a whole, right, we've got less going up toward the atmosphere. So more is running off. There's going to be more flooding, right? It's going to be more flooding when we have urban landscapes. It's going to be less water getting down into the ground, all those kinds of things. Cool. All right. So what do you think we use water for the most in the U.S.? Any thoughts?
Production,
Okay, so yeah. So,
processing products.
okay, so processing of food products potentially. Agriculture. Uh-huh. Yeah, good. What else? Recreation. Uh-huh. Yeah, and right. So thanks for bringing that up. I should have mentioned I'm thinking of things that consume water here. So we definitely use water for recreation. But the way these data were set up, they're looking more like things that we use up water to do, which I guess could be recreation, like a water park or something. I don't know. Okay, yeah. So we've got maybe industrial food processing, stuff like that, agriculture. So if we were to list all the different things that we use water for in the U.S., we could look at irrigation, thermoelectric power. Do y'all know what we mean by thermoelectric power? So basically, whenever we make electricity, we like to do it by creating steam. Right? So you generate steam, which turns a turbine. So you need to heat up water. And we can do that either by burning coal or by burning natural gas. And then there's other ways to do it too. But thermoelectric power is where we heat up water to produce electricity. Okay. So all these categories: irrigation, thermoelectric power, the public supply. That's like what comes out of your tap, right? Industry, so different kinds of factories. Livestock and aquaculture. Do y'all know what aquaculture is? So when we're raising like stuff that lives in the water, essentially, right? So like if you're farming fish or mussels or that kind of thing. So we've kind of got like two agricultural categories: irrigation and livestock, aquaculture. Then domestic that isn't public supplies. This would be like well water, and then mining. So which of those do you guys think is the greatest? The largest? So livestock, Irrigation. So it turns out that the two largest, I actually had them in order, that irrigation and thermoelectric power account for about 80% of our use. So agriculture, if we sum them up, right, is our largest use of water, right? So about 40% of our water use in the U.S. goes for irrigating our crops. And then another kind of small fraction for livestock. It's interesting though. I mean, the thing about livestock, often they'll often graze in existing water bodies. So I think that's why this is looking at more like water extraction. So this wouldn't take into account like if livestock are feeding in a pond or drinking from a pond, for instance. Okay. So I just think it's really interesting, right? Again, it points out just how important like the agriculture sector is, right, to what we do, to the environmental sort of footprint of our society. Also, who knew, right? If we use less electricity, we're conserving water because we use so much water to produce electricity. So it kind of highlights the importance of food production and energy production, right, to our country's economic footprint, environmental footprint, or economic too. Any parts of that that are surprising to you? Any numbers here that surprise you? You're like, man, nothing surprises me anymore. Could be anything. All right. So I want to talk just a little bit about groundwater. Groundwater is about a quarter of U.S. Water withdrawals. So we use groundwater. What we use it for the most, like other water, is irrigation. And so this is showing rates of groundwater depletion, right? So you could probably guess, what's most of the water being extracted to be used for here?
Agriculture?
Yeah, agriculture. So places where we're using a lot are places where we're farming a lot. So if we were using, so we've got a water cycle, right? We've got water that's getting its way into the ground every day, whatever rates of water getting to the ground. Let me ask y'all, if we were using groundwater sustainably, what would our groundwater depletion rate be if we were using it sustainably? Yeah, so if we were using groundwater sustainably, we'd be using it at the rate that it's replenished, right? So if we were using groundwater sustainably, in fact, we wouldn't be depleting it at all. But since we are depleting it, then we know we're using it at a rate faster than it's being replenished. Does that make sense? Cool. Have you all ever been in a plane and you look down and you see these weird, like, green circles? If anybody's flown to California, my my brother's in San Diego, my sister's in San Francisco, and we went out to visit them. And as you're approaching those areas, there's not much water. It's fairly dry, but you'll kind of see these like green circles on the land. Anybody ever notice that? Crazy, right? Well, what's happening is that these are areas that are pretty dry. It's not raining a lot. That's why the surrounding land doesn't have anything growing on it. And then these circles are where they have what's called center pivot irrigation. They do this a lot out in Nebraska. And so they have these big contraptions on wheels that will turn. It's like the spoke in a wheel, or sorry, yeah, like the spoke in a wheel. It'll kind of rotate like this, and it will be spraying water as it does. So you can create all these little kind of circular patches of green. And, you look at this, and it's a lot of water. So that's, pulling water generally up out of the ground, pumping it up, and then putting it on the land. So you look at the surrounding landscape, and it's dry, right? There's not much growing there. But we have to put a lot of land on there, a lot of water on the land to be able to grow stuff. Just as one example, in the Ogallala Aquifer, what's an aquifer? Have you heard that term before? I say aquifer, you say something I need to know for our exam next week. Well, yes, but besides that. So an aquifer is just a concentrated underground source of water. They're not like underground lakes. This isn't like a giant cavern like you'd see in like an Indiana Jones movie, and you can like take your boat through it. But it's groundwater that we can get to. It's largely permeable rock, so something like sandstone that can get saturated with water, then we can extract the water. So this aquifer here, this actually used to be a giant lake. Like way back millions of years ago, a lot of the central, how should I say this? The southwestern U.S. into kind of the western U.S. used to be a giant lake. As that lake dried down, the water went underground, essentially. And so that's why there's all this groundwater that's accessible. And there's a lot of it. In some places, it's like 300 meters thick. That's a lot of water. It's a pretty thick layer of water. But we're pumping water out of there pretty fast. In some cases, we're pumping water out of there 40 times faster than it's being replenished. So we were talking the other day about how it's possible to use more energy than an area would naturally produce in a year. Right? And so you have to get at sources of energy that are not easily accessible. And so these areas are producing a lot more agriculturally than they normally would for several reasons, right? Like we're putting more fertilizer on the land. So we're sort of short-circuiting the nitrogen and phosphorus cycles, right? We're producing that faster than nature would. But then water as well. There isn't enough water that falls out of the sky in a given year to produce all the crops that are being grown there. So what we do is we pull water up out of the ground. And we can do that with technology, because remember, technology increases our access to resources. But there's going to be a limit, right? When I was living in Texas, there would be sometimes when we'd have a really dry summer, they wouldn't allow you to water your lawns, for instance, because those would be times when water would be getting scarce. Actually, a funny story. I inherited a lawnmower from another professor at Austin College because he turned his whole yard from grass into like a rock garden because he was tired of like, one, trying to keep enough water on it so the grass wouldn't die, and two, having to mow the lawn all the time. So got a lawnmower out of the deal. It's like, you want a lawnmower? Don't need this to mow my lawn anymore because I don't have a lawn. But that's what the natural landscape is, right? Because you think to yourself, gosh, I got to go out like every couple of days and spray water on my grass. That just tells me that that's not a plant that would normally be living there, right? So on the other hand, if you just have like cactuses and some bushes and things like that, they're going to live there naturally, not going to have to put water on it, and heck, you don't need a lawnmower. All right. But there are ways to use water more efficiently. So if we look at this, see all this water spraying everywhere? Dude, it's like 90 to 100 degrees out when they're doing this. So you know where a lot of this water is going, like back in the atmosphere, right? So to use it more efficiently, there are a few things we can do. One of these is called drip irrigation. So it's the same kind of contraption. It's got this wheel, so it's a center pivot device, so it's kind of rotating around like this. But now, instead of spraying the water out, we've got little rubber tubing that comes all the way down to the ground and makes sure that the water drips directly down to where the plants are. So, there are ways that we can use water more efficiently, and still kind of be growing the same stuff. All right, so that was a little bit of groundwater story. So surface water, right? The part that's active in the water cycle. It's been estimated that humans now appropriate about 54% of all accessible surface runoff. So think about that. A drop of water falls to the earth. There's a 50-50 chance that that water droplet, is surface runoff, is going to get used by people. That's a pretty dramatic impact, right, on the water cycle? And we do it a lot of different ways, like we create canals like this to move surface water around. Not a real awesome idea, because this is out. So looking at this picture, do you see a lot of plants in the landscape here? It's a desert, right? We're moving a whole bunch of water in a canal in a desert. That water, man, it's evaporating fast. But we're moving that water to some place where we're trying to, it's probably Las Vegas. I don't know. Maybe Las Vegas or LA. Who knows? We're moving water in the desert because we've got people living somewhere that's dry. Or we're trying to grow crops somewhere that's dry. And we have a history of using too much water. So the LC in Eastern Europe, Lysenkoism was this idea of agricultural production that was crazy. Lysenko was an advisor essentially to Stalin, an agricultural advisor, had some crazy ideas. But one of the things that was happening was they were growing cotton, which is a very water-intensive crop, in a place that didn't have a whole lot of water, this place in the Aral Sea. So they had to extract water from the Aral Sea, which was actually fresh water. This is Eastern Europe is where we are right now. And because of that, right, extracting water from this lake, growing cotton, harvesting the cotton, selling the cotton, that's essentially exporting the water as cotton, if that makes sense. These cotton plants are taking the water, turning it into cotton, they're getting exported. So there's that loss of water. So as a result, the sea shrunk dramatically. And so we now have boats, for instance, where there's no water left. This is also an environmental problem from another perspective, because there was a lot of industrial pollution going on in this area as well. And it was getting washed into the lake. When the lake dried, now you've got dry, dusty area with pollutants in the sediment, windy, and bad thing. All right, so if we look at where people live on the planet and where the surface runoff is, a couple of interesting patterns emerge. So we can look at Europe, Asia, Africa, the Americas, Australia, and Oceania. And we can look at the share of the global population versus the share of global river runoff. So for instance, we see that about 60% of the world's population lives in Asia, but only about 35% of the world's river runoff is there. On the other hand, it's only about 5 to 6% of the world's population in South America, whereas there's about a quarter of the world's river runoff there. So what this means is that we don't have an even match of people and water. So just there's a couple places to contrast there. Asia is a place that is really having some water challenges now because there's just not as much runoff there compared to the amount of people. South America, on the other hand, is very water rich and, relatively speaking, fewer people. So, like ourselves as a people, like humans, we kind of have to learn like humility from time to time, right? And we'll often go along kind of thinking that like we're in control, we know what's happening. Then either something crazy like COVID happens, which shows us that actually no, nature is kind of ruling over us, or something like our dependence on water. A simple resource like water shows us that, in fact, we in some ways still sort of live at the mercy of nature. So it's interesting, the ancient city of Angkor, Cambodia. Anybody been to the ancient city of Angkor, Cambodia? Oh man, I'm still waiting for somebody. Sometimes I've been there. Anyway, actually I have a friend who worked there. He was with the UN. But this is the largest pre-industrial city in the world. And it had a pretty good run from the 9th to the 15th century, so 600 years. How long has our country been around? 240 years? Okay, this city was going for 600 years. Not bad. And it had a really elaborate system of reservoirs and water distribution. It was a Buddhist kingdom, actually. There's some really interesting temples and stuff there. Well, it turns out that what led to the downfall of the city of Angkor was the climate. So you can do this really interesting thing about looking where you look at the rings in a tree and you learn about the history of the climate. Have you ever seen a tree that's been cut and you kind of see all those rings? And because trees grow fast during the summer and slow during the winter, there are sometimes when their growth rings are spread out and sometimes when they're compressed. And so because of that, there's a ring every year. So when you cut a tree then, you can count the rings to see how old it is. But that's not all that you can do. You can also look at the rate of growth and learn about the climate. You can even do some really cool things. There's a professor in our department who does research on soil contamination. And you can even look at the tissue of that tree when it grew, say, 20 years ago, and you can see if the tissue has contaminants in it. And he used that technique to see how many years back this particular area was being contaminated. So you can learn a lot from trees. And you don't have to kill them to do this. You can take a tree core where you just kind of drill in from the side, and you can do it. So you don't actually have to cut it down. You can, if you know how to do it, you can actually drill in from the side and collect the same data. I don't think the tree really likes it, but that's what it is. All right. So some trees, y'all, can live to be thousands of years old. It's crazy. Just like think about that for a while. Trees can live to be thousands of years old. So when they look at tree cores with some of these trees, what they found was that the city was doing great until there was this shift in climate. And it was actually a global shift in climate. It was known as the Little Ice Age. It happened in what's called, the time also known as the Middle Ages. So this is a drier climate. All of a sudden, the city, that's when it disappears. Another example, this is in Mongolia. So these Siberian pines can live to be 2,000 years old. So this is kind of an interesting study. Y'all have heard of Genghis Khan? Famous for what? The largest land empire or largest contiguous land empire in history, or something like that. Known as like an incredible military leader, all these sorts of things, right? Well, he might have had some help. This is a professor at the University of West Virginia who similarly was able to reconstruct the climate from looking at the history of the tree rings in these Siberian pines. So the 13th century Mongol Empire was the largest contiguous land empire in world history. So they were able to reconstruct this temperature regime. And the results indicate that the regional climate during the conquest of Genghis Khan, I guess it's more correctly spelled Chinggis Khan, that this Mongol Empire was warm and persistently wet. Now, they were going around with horses in these high elevation plains of Asia. That area is in the Himalayan rain shadow. It's on the other side of the Himalayas. So when the moisture comes from the Bay of Bengal, it slams into the Himalayas, it creates a monsoon. But on the other side, there's almost no rain. So they were conquering these areas. They were very dry. What just happened, that when they were going on all these horses, everything else, was a time which happened to be warm and persistently wet. So this is a time that was very good to be going around with horses and armies. This period, characterized by 15 consecutive years of above-average moisture, coincided with the rise of Chinggis Khan. That particular time was unprecedented over 1,000 years. So yeah, I'm sure he was a heck of a military leader, very strategic, all those sorts of things. Also, had a bit of a kind of pick-me-up from nature at that time as well. So again, the importance of nature and natural cycles in our human history is pretty important. And so just as sort of an aside, something else that they found, similarly, the early 21st century drought in central Mongolia was the hottest drought over that entire 1,000-year history, right? So just as that time was very good for productivity, the drought that was currently happening in early 21st century Mongolia was the hottest in the last 1,100 years. So I think that helps put into perspective, too, kind of the climate now that we're dealing with, right? So, so that was also sort of unique. Cool. And just one final thing here, and then we'll wrap up. If you all remember the Arab Spring several years ago, it was a time of uprising across the Middle East against governments. Well, there's a link here, but I'll just kind of hit you with the bullet points here. These times of revolt were linked to a few different things. Part of it was government created. So the government supported a policy of unsustainable agriculture, which led to groundwater decline. What that meant was that people out in the rural villages no longer had the water that they needed to survive. Okay, meanwhile, in 2006, 2007, there was a severe drought. So on top of that unsustainable water use, there was now a severe drought that kind of pushed it over the edge. As an aside here, the severity of that drought can only be explained using anthropogenic models of the climate, right? So the severity of that drought can only be explained, the severity of that drought cannot be explained using just natural mechanisms. So in other words, this is a consequence of sort of human-directed climate change. That leads to 2 million people migrating to urban areas during this time. And that led to civil unrest and then ultimately rebellion in a lot of these areas. And it's going to be about the history in this time, but this was in Syria with President Assad, where there were these massive revolts, and in other countries as well, Arab Spring. So I just think it's really interesting, you know, water is kind of one of those points of connection between the environment and human history. And I just think it's important for us, as we sometimes say, oh, you know, like, are the things that way the environment is being impacted, like, we're able to deal with it, like it's not a big deal. Well, throughout history, it's kind of been a big deal. And I don't know, just to me, one of the things COVID shows me is that we don't always know what's in the environment and how it's going to affect us. And that as we affect it more and more in different ways, it's hard to tell what's going to happen. So, oh, and the one thing I wanted to mention was this is actually research that was done by a UNCA grad. His name's Colin Kelly. Okay, so I think I'm going to wrap it up there.